package. How far along the ground will the package strike the ground? Same problem, but with a upward angle of 20 degrees. All right, so ground. I don't really care about the plane, it's the package we're interested in. So the package has an initial velocity, just exaggerating it a bit, angle of 20 degrees directed downwards and 240 meters per second, so it's really moving. And they are 15,000 feet in the air. So I will, there's nothing fancy about this question. It's where along the ground it lands. So all it wants is the range. I don't see a lot of point in doing the entire problem because most of the time it's just laying out the information that's an issue. But it'll help me if I find out that the reason you can't do this is because you can't find like the time or something silly like that. But that's a algebra 2 issue. So the vertical is delta y. The initial y velocity, v naught, y naught, vy, a, and t. Horizontal will be delta x, vx, and t. As brought up yesterday, which we reiterated, there is a way through trig to figure out the two velocities. This will be v naught sine the angle, and this will be v naught cosine the angle. I see no reason not to go back through that. The acceleration is gravity, so 10 meters per second squared. And the package has to fall 15,000 meters. So you asked, do you want upwards to be positive or negative? Fine. I don't care. You just pick. Is up positive or is up negative? So if up is positive, then that's negative, and that's negative, and that's positive. Right? Because the package was dropped at an angle that was declining. So the initial velocity is downwards. Doesn't make much of a difference. The second question just reverses this to be a positive sign. So it's not that different either way. So the next step would be to figure out the two velocities. So I'm going to do 240 sine 20. I'm trying to be very clear. I'm not trying to be difficult. The negative 20 was so you understood that the plane was in a dive and the angle was below the horizon. However, we're using that angle to figure out a velocity. We have to decide whether that velocity will be positive or negative. Right? Now, my understanding is that you guys probably maybe just blindly put negative 20 into your calculator and hit the sine function, which will probably give you a negative for an answer because sine is negative in quadrant 4. I understand that. Now, if you don't understand that, I'm not asking you to. I'm asking you to draw a picture and consider what up and down means and decide whether a downward angle for the plane would result in a upwards velocity or a downwards velocity for the package. I'm telling you to forget some of the stuff, not forget, just leave out some of that blind memorization you have for math stuff and look at the reality of what the question is attempting to communicate to you. So what do you think? Should you put in the negative 20 there or not? If you put the negative 20, it's going to result in a negative sign out in front anyways. That's assuming that you made downwards negative in the first place. I would just be careful about what you do with that positive or negative. Fair enough? All right. A basketball player's hang time is considered the time when they appear to float in the air while going up for a dunk. Consider a player who is going to jump a maximum height of 1.2 meters above the ground while traveling 4 meters along the ground. What must their launch velocity and angle be? Compare how long they spend in the top half of their jump with the time they spend in the bottom half of their jump. So there's different parts to this problem. I'm not sure all of this problem can be done using the information as it's been presented. But I get the impression that the basketball player jumps from the ground and lands on the ground. Something like that. And their displacement is 4 meters. And their maximum height above the ground is 1.2 meters. But we were never given their launch velocity. In fact, we're being asked their launch velocity. And then we're also being asked questions about like how long they're in the air. These seem like different questions to me. So if I was to try and articulate what's been given, it is quite possible I might screw this part up if I'm not being super careful. For example, let's take a look at what we might believe is being given in this problem. And again, I'm going to start with all the same pieces. The basketball player lands 4 meters away from where they start. But we don't know their horizontal velocity, and we don't know how long they're in the air. So that's about it for the horizontal part. It's gravity that pulls them back down after they jump into the air. And if they land back on the ground, that's 0. I've got that. I think that's it, right? I don't think we can solve anything with that. I mean, there's not enough information on either side to turn this into a problem. We may have to change how we're shaping this problem. And there's information we didn't use, correct? The 1.2 meters. So is there a different way we can come at this problem, perhaps to try and find out what's been missing or what we don't know? Yeah? Okay. Is their path symmetrical in the air? Actually, I think we do know. Because their path has to be parabolic, right? So the up and down part has to be symmetrical. So if I use what you're saying, I certainly could consider half the flight of the object and assume that we're talking for right now not about the whole trip, but about this portion of the trip. That will change my displacement to be at the 2 meter mark. And that gives me a slew of other information I didn't have. For example, it means that I can use the 1.2 meters. But I also know that you reach this maximum height when the final velocity is 0. That gives me a bunch of information that I can use now. For example, I have 3 pieces of information. Should I decide to make upwards positive again and to the right positive again, then I can put a plus here, and a minus there. And that is 3 pieces of information on the left. I could determine this velocity, and I could determine the time. Well, that's kind of what we wanted. We wanted the actual velocity. We want V naught, and we want theta. Determining Vy naught doesn't tell me either the angle or the speed. You understand that, right? It tells me just how fast they left the ground. It tells me V naught sine theta. So there's a lot of combinations of V naughts and thetas that would give me whatever that number is. So I don't have a way to solve it directly, but if I do find the time, I could use it to find V naught cosine theta. Now, once I have both of those, I think there's probably a way to figure out V naught and theta. Would you guys agree with that? Do you need me to go further with this one? Like maybe you don't know what to do once you found those two, or do you kind of have an idea of what you could do? Go ahead. let's say we do get a number for these two things, correct? Well, V naught sine theta divided by V naught cosine theta will be tangent theta. Does everybody see why that must be true? The V naughts cancel out, and I get sine divided by cosine. That's got to be tangent. So if I have a number for those, I think I can use that to figure out what theta is. And once I have theta, I can go back then and figure out what one of the V naughts is. Does that seem like a good plan? Now, that's not the only part of this problem. There's another part of this problem, and I think that's going to take you a little more time to solve, but I don't think you can use most of the information that's here for it. The other part of the problem about the time it takes to fall, or time that they're in the air, I would consider that you have the upwards y velocity, Vy naught, right? You have that, and you know that halfway into the air is 0.6 meters. You know that too, right? And that the acceleration will be acting at 10 meters per second squared downwards. That's 3 pieces of information. You can probably figure out how long it takes to get to the halfway point. Right? Double that, and that's the amount of time they spend in the bottom of their jump. And since you have the entire time to get to the top, you could probably figure out how much time they're spending in the upper portion of their jump. Just subtract, right? And that would give you the time they're spending in the upper portion of their jump. Double it, and that would be the time that they spend in the total upper part of their arc. Is that okay? Or do you need me to do more of this? I don't think it makes a difference. You're going to need both.
All right. So you can go either way.
It will be the same problem. Is there anything more about 3 I have not covered that gives you something to work from tonight? Okay, so now number 7. Is that what you want, Brianna? Going to have if we look at number 7 and I see what it says, as the batter hits a pitched ball when the center of the ball is 1.22 meters above the ground. The ball leaves the bat at an angle of 45 degrees with the ground. With the launch, the ball should have a horizontal range, meaning returning to the same level of 107 meters. And it tells you to use this to get the ball's launch speed. I think they're telling you that delta y is 0 in this instance, and that delta x is 107, and that you're launching at an angle of 45 degrees. You could use the range equation there. I mean, you could probably also use the chart if you wanted, but it would be harder. But I think you could use the range equation to figure out what V naught is. But then be careful, because the next part is asking if you clear a fence. And in clearing the fence, you're already 1.22 meters off the ground when the ball is hit. And the fence is 7.32 meters above the ground, a distance of 97.5 meters away. So you need to have a delta y that is 7.32 minus 1.22 to clear the fence, because you're already starting 1.22 meters above the ground. Or you take delta y and split it up into y minus y naught and put for y naught 1.22 meters to indicate that the starting height above the ground is 1.22 meters. And then find out what the height of the ball is when it's 97.5 meters away. That was yesterday's quiz, so I think you could do okay on that part. Is that all right? Is that okay for everybody else? I mean, that's what it's stating when it says it returns to the launch height. So delta y is 0 for that instance of the problem. So, So let's set up the problem, and you guys tend to not like doing this, but just draw a picture. I mean, there's a lot here that you can use to kind of help set up what this problem looks like. So I get the idea that we are 18 feet from here, 18 meters from here to here, because it says it's a 9 meter square on each side of the net. And the net being in the middle, something like that, I guess. And the person who is serving probably jumped so that they're hitting the ball 3 meters above the ground. With a perfectly horizontal velocity. This is 3 meters. This is 2.24 meters. And that's what we've got. And this is 1 meter. So I foresee that there are two speeds. If I hit it too softly, it goes like this, right? And if I hit it too hard, it goes out of bounds. So we're looking for what minimum speed would get the ball to make it just to the top of the net, and what maximum speed would keep the ball in bounds. So I just see two problems here. One where the delta y is relative to the net, but the horizontal distance is 8 meters. And one where the delta y is all the way to the ground, but the horizontal displacement is 17 meters. Does that make sense? Ethan, what do you think of that? Is that enough for you to do the problem, or do you want me to go more? Sure. I would probably break this up into two problems. Make this one our minimum one. The minimum speed that the ball needs to have to make it over the net. And be careful about problems that talk about minimums and maximums. The truth is, we don't want the ball to hit the net. Oh my God, what's the problem here? Mr. Shelton, when your technology fails you, you have no patience. Okay. I'm afraid I need new technology. All right, that's gonna have to be good enough because things are not going well. All right, so vertical, horizontal, vertical, horizontal. Delta y here is gonna be 2.24 minus 3. V final minus V initial. V initial being 3, V final being 2.24. This assumes upwards is positive. I'm looking for the initial velocity, but it says it's hit perfectly horizontal. And acceleration, gravity. On the other side, delta x is, well, how far away are we from the net? They say we are 1 meter into the court, right? So we are 8 meters from the net, so delta x is 8 meters. We want this speed. So find the time on both. My chair's a little bit in the way. For the maximum, well, the maximum, want to keep it in the court. So my delta y is now 3 meters. Well, better, 0 minus 3. Final position 0, initial position 3 meters above the court. This again assumes upwards is positive. Initial y velocity, again, 0. We said we're shooting with just a horizontal velocity. Acceleration, still 10 meters per second squared. Probably should make it negative if we're going to be doing that. And then my delta x is going to be, well, it's going to be 9 plus 8, so 17 meters. This is going to make it all the way to here. And we are looking for Vx. And again, time is probably the thing that links these two problems together. I really can't do any more unless I just get the numbers for you. So, is that better? All right. A ball, this is number 7. For those of you watching at home, this is number 7 again. Because it's all one big problem. The player, assuming standing, say, 1.2 meters, swings the bat, striking the ball above the ground 1.22 meters. If we are to draw a horizontal line from 1.22 meters along the ground, they tell me that the ball travels 107 meters before coming back to this very same height of 1.22 meters. That's just a setup in the problem so that you have enough information to figure out what the launch velocity is. But that's what they're telling us in this question. Is that if there was nothing in the way, like, I don't know, a wall, that's where the ball would make it if it were coming back to the same height. But there's a wall, 97 meters. I don't know what's going on with my stuff. Mr. Shelton is going to freak out. Thank you. There's a wall somewhere over there that Mr. Shelton can't even draw or mess with, whatever. He's kind of done. There's a wall here. And we don't know if it's going to make it over the wall or not. That's what the next question is about. The wall's only 97 meters away from where you hit the ball. You want to see if it'll make it over the wall or not. Be careful, though. The wall is 7.32 meters tall, and the ball is starting 1.22 meters above the ground. Your ball needs to have a vertical displacement of 6.01 meters to clear the wall, right? Relative to where you hit the ball. That's what it's talking about.